In the previous case we said a relationship exists between stress and strain. Now we said could be of any form. Now we are going to restrict further, saying that it should be linear. Okay. So homogeneous, then we said isotropic, then we said elastic, but not general elastic, linear elastic. So material is linear elastic, not any general elastic. What does it mean? Okay. So we will discuss this linear elastic with respect to normal stress and shear stress. Those are the two graphs shown here. The first graph plots normal stress versus normal strain. A general relationship is shown here as a curve here, but the relationship is linear up to a point tau xx p, that is a limit within which tau xx the normal stress is linearly related to the normal strain. Beyond that it becomes non-linear. So our limit of applicability of Hooke's law is within that region where the stress strain relationship, normal stress normal strain relationship is linear. Okay. Now how do we experimentally get this data? Okay. Remember we said we are going to find the constants, the material properties by means of experiment. As I told you, what we are saying is the form of the expression is taken by us. For example, in this case linear, tau xx is equal to or tau xx proportional to epsilon xx, and the proportionality factor is the Young's modulus, which is E, but how do you determine this is by experimentation. We are not going to predict Young's modulus, we are going to experimentally determine Young's modulus. Okay. Okay. So let us see how do we do this. We consider, let us say, a rod and then subjected to uniaxial stress. What do I mean by uniaxial stress? You apply stress, a normal stress along only one direction, that is why it says uniaxial stress. Okay. Material subjected to only normal stress tau xx, and then all other stress components are 0. We have tau yy, tau zz, tau xy, there are no other normal stresses, there are no other shear stresses also. That is what we mean by uniaxial stress. There is only one normal stress along one particular direction. In this case we are considering tau xx. Okay. Now how do we carry out the experiment? You apply a force and then divide by the area of cross section, you get the stress, so which is your y axis, and for every force applied you determine the change in length by original length, which will give you the strain, and you plot this graph. Okay. So you take the, let us say, a rod, apply a tensile force and express the force as stress by dividing by the cross section area, and measure the change in length, and change in length by original length will give you the strain. Now when you plot, as we have discussed, we will restrict only to the linear portion of the curve, and where tau xx is proportional to epsilon xx, and the proportionality factor, or in this the slope of this curve is E, which is the Young's modulus. So tau xx is equal to E into epsilon xx. You, as we proceed, we will express stress in terms of strain and strain in terms of stress. So we also express the this relationship as epsilon xx is equal to tau xx by E. So first is tau xx proportional to epsilon xx, and the proportionality constant is Young's modulus. You also write this expression for epsilon xx as tau xx by E. Okay. And E is the modulus of elasticity or Young's modulus, which is very well known. In fact, the Hooke's law, which is very well known to everybody, is this form of Hooke's law is very well known to us. We are going to extend this to 3-dimensional case. Okay. The Hooke's law, which is this for a 1-dimensional case subject to only uniaxial stress, that is only subject to only normal stress. There are no other normal stresses, there are no normal stresses in other direction, there is no shear stress. we are going to extend this to a 3 dimensional case where there are normal stresses acting in all the 3 directions and shear stresses as well. Okay. So, that will give you idea of what is that we are proceeding towards. Okay. Now, we will discuss analogously for pure shear stress. Okay. We discussed the case where there is only normal stress along only one direction. We will discuss now for the case of pure shear stress. Okay. Now, what do we mean by that? The material, let us say you have a plate what do we mean by pure stress shear stress? We have a material and then we subject it to pure shear stress. Of course, something like squeezing this and so material subjected to only shear stress and all other stress components are 0. So, we have only tau xy, tau yz, tau zx they are not there and the normal stresses tau xx, tau yy, tau zz they are also not there. Taking a plate and subjecting it to only shear stress, okay. Let us say in the xy plane. Now, you are measuring the and whatever let us say you apply the force expressed per unit area and that is the shear stress on the y axis and you measure the change in angle. Remember we defined gamma xy as the difference between pi by 2 and the angle in the final state. So, you measure this angle which is the shear strain and that is the x axis. So, you plot a graph between these two, that is the shear stress which you applied and the shear strain which you measured and you get a relationship. Now, just like the graph between normal stress and normal strain, you get a general relationship which could be non-linear, but like in the previous case we restrict to a point where the shear stress shear strain relationship is linear and that relationship is expressed as tau xy is equal to g into gamma xy. So, tau xy proportional to gamma xy in the linear portion of the curve. What is the proportionality constant is denoted by g, which is the modulus of rigidity also called as shear modulus. So, in terms of understanding, Young's modulus is very well known to us, which relates normal stress and normal strain. G is a modulus of rigidity or shear modulus which relates shear stress and shear strain. Okay. Just like we expressed the previous relationship for normal strain, we also express this relationship for shear strain. First expression was for the shear stress in terms of shear strain, second expression is for shear strain in terms of shear stress. As I told you, as we go along we will use both the relationship few times. Okay. And in terms of significance, let us say a material has very high Young's modulus. What does it mean? For the same, suppose let us say you subject two material to the same tau xx, the material with higher Young modulus will have only a very small value of normal strain. Similarly, if you have two material and then subject to the same shear stress, the material with higher modulus of rigidity will show a smaller change in angle. Okay. So, that is the significance of E and G. Okay. Higher the value, lower the strain. Okay. Now, we have discussed the two material properties, one is Young's modulus, other is shear modulus. We will discuss one more material property which is Poisson ratio. So, now I think it should be clear to you what we really meant by material property. When we discussed homogeneous material and then isotropic material, we discussed about material property. These are the material properties: Young's modulus, shear modulus, Poisson ratio, etc. Okay. Now, to explain about Poisson ratio, we will once again consider let us say a cuboidal block, a block is cuboid in shape, subjected to normal uniaxial normal tensile stress. Uniaxial meaning there is only one normal stress and in this case it is tensile stress. Okay. That is what is shown here, and you are shown a element which is subjected to uniaxial normal tensile stress. Okay. Now, and that is shown magnified here, the length of the element is delta x, okay. The height is delta y and the width is delta z. Okay. Now, that is the those are the dimensions in the initial state. Now, this subject to normal tensile stress, and then it undergoes deformation. In the final state the dimensions have changed. Okay. Now, let us look at the length. There is an increase in length. Okay. Delta x has become 1 plus epsilon x into delta x. How did I write that? Delta x is the original length. What is epsilon xx? Epsilon xx is change in length by original length. So, epsilon xx into delta x will give you the change in length. When you sum up, will give you the final length. Okay. Just let me repeat, express this as delta x, the first term, which is the original length. Epsilon xx is the change in length by original length. Epsilon xx is equal to change in length by the original length. Okay. So, the change in length is epsilon xx into the original length, which is delta x. So, when you sum up these two, you get the changed length, okay, or the new length. Now, what happens if you subject, let us say, a cuboid to tensile stress along x direction? There is decrease in the height and the width along the perpendicular direction. Okay. So, we will use two terminologies, one is direction of stress, other is perpendicular direction. So, in this particular case there is elongation, there is increase in length along the direction of stress. There are two perpendicular directions, one is y, other is z. Along those directions there is decrease in the dimensions of the height and the width. Okay. Let us see that. If you look at the height, the original height was delta y, and that has become this height, which is 1 plus epsilon y y into delta y. Coming to the width, the original width was delta z, and the new width is this width, which is 1 plus epsilon z z into delta z. Okay. These have been written similar to what I have explained here. Okay. So, to begin with, we had a cuboid of dimension delta x, delta y, delta z. You applied a uniaxial normal stress along the x direction, the direction of stress, and there was elongation along the x direction, increase in length. Because of increase in length along x direction, there was a decrease in the height and the width along y and z direction. Now, okay, what we have discussed is for the case where epsilon xx is greater than 0 because increase in length, and epsilon yy and epsilon zz are less than 0. Other case is also possible. For example, there could be, when you are applying, let us say, a compressive stress, epsilon xx could be less than 0, and other two can be greater than 0. The strains in the other two directions can be greater than 0. Okay. Okay. But throughout our discussion, we will consider the case where epsilon xx is greater than 0. Okay. Okay, that is what we have discussed: extension in x direction, contractions in y and z direction. Okay. Now, for a linear elastic material, it has been experimentally observed that the normal strain in the perpendicular direction is proportional to the normal strain in the direction of stress. What is the direction of stress? X direction. Epsilon xx is the normal strain in the direction of stress. What is the perpendicular direction? Y direction. One of the perpendicular directions, y direction. So, left hand side is normal strain in the perpendicular direction. Experimentally, it has been observed that epsilon yy is proportional to epsilon xx. what is the proportionality constant is nu, which is the Poisson ratio. Now, we have seen that when epsilon xx is positive, epsilon yy is negative. So, to account for that we have a negative sign here, so that the material property which is Poisson ratio is positive. Okay. We do not want a material property which is negative. We have positive Young's modulus, we have positive shear modulus, we do not want to have a negative Poisson ratio. So, we take that into account in writing the relationship itself. Okay. So, just to repeat this, based on that is why you see what did we say, stress strain relationships are empirical. Why? Because it is based on experimental observation. We cannot derive this linear relationship. Okay. We can only based on experimental observation write this linear relationship, and the proportionality factor nu has to be found by doing experimentation. Okay. So, both the form of the expression and the constant is based on experimental observation. Okay. And so, to put this in statement, nu is a Poisson ratio. Okay. So, this is the statement for that equation, strain in a direction perpendicular to an applied stress is proportional, of course opposite sign to the strain in the direction of the stress. Okay. So, in this particular case, strain in the direction of the stress is epsilon xx, strain in the direction perpendicular to applied stress is epsilon yy, they are proportional, and the proportionality constant is nu. Negative sign is introduced to take care of when one undergoes extension, other undergoes contraction, or when you have extension in one direction, there is contraction in other direction. Okay. Similarly, you can write for the normal strain in the z direction is proportional to the normal strain in the x direction, along which you applied the stress. Proportionality constant is nu. Okay. And remember, we said isotropic material. See, we have used the same nu for both the relationship. We have not given two different nus, which means that we are assuming nu, the Poisson ratio, to be independent of direction. Okay. If it were depending, then we should use different nu here. Because we are assuming material properties to be independent of direction, because we are assuming material to be isotropic, we are using the same nu here. Okay. Now, suppose if we subject a body to a uniaxial normal stress, what are all the strains? What are all the strains? Okay. Along the direction of stress, we can write epsilon xx is equal to tau xx by E, which is what we have seen in the previous slide. Okay. That is why I told you we will use both form of the relationship. We will write stress in terms of strain, also strain in terms of stress. Okay. So, this is the relationship which we have seen in the previous slide, writing normal strain in terms of normal stress. So, this is the normal strain along the direction in which the stress has been applied. Okay. Now, there are two perpendicular directions. So, the normal strain along y direction is minus nu times epsilon xx. So, minus nu epsilon xx is tau xx by E. Similarly, you can write for the z direction, which is another perpendicular direction. So, strain in the z direction is equal to minus nu into epsilon xx, and epsilon xx is tau xx by E. Okay. So, what is the meaning of this statement? If you have a let us say a cuboidal element and subject to uniaxial normal stress along x direction, then the normal strain along x direction is given by this expression, and normal strain along y and z directions are given by these two expressions. Okay. So, that is the meaning of the last statement. Okay. So, to summarize the last two slides, we introduced we discussed what do we mean by linear elastic material. We said linear elastic material is a material which has a linear relationship between stress and strain. We said we discussed the linear relationship for normal stress and normal strain, also for shear stress and shear strain. These two introduce two material properties, namely Young's modulus and shear modulus. Now, we discussed another material property, namely Poisson ratio, which relates strain in the direction of stress to the strain in the perpendicular direction. Okay. And what we have seen, this line, the equations here are the, when you subject a body to a uniaxial normal stress, what are all the strains in the 3 directions. Okay. One strain along the direction of stress and strain along the perpendicular directions. Okay.